gradient descent. And it's a very ancient algorithm. It started at maybe 60s. So it's at a very early stage. But people soon just discard this method because this method requires a lot of precision. At that time, you do not even have float precision. So in that case, the algorithm is not stable. So nowadays, we usually have double float precision, so it's fine. And on the past 10 years, people find that, okay, this method is really good at text classifier. So if you have a very large feature space, and for example, on some text classifier, you want to sparsity, and this method works very fast, and it's usually fast than LBFGS or stochastic gradient descent something. So today, I'm going to talk a little bit about what is gradient descent and its relationship to yesterday. Sylvia said, okay, proximal gradient descent and how to parallelize these things and how to distribute onto multiple machines. So let's start. Okay, so let's start with lasso. So it's a very easy problem. So given that okay, we're going to solve this problem. So in fact, it's quite easy problem because this is a quadratic term, and this is the difficult part because it's non-smooth. So the gradient descent says, okay, if we cannot solve the whole problem at the same time, we can fix all gradient except one and solving a one-dimensional problem at each time. So you just the gradient descent is quite simple. Each time you pick up gradient I and fix all that rest gradient and solve this problem. So we can easily say, okay, assume this is F. We can know this is a delta equals to, because it's a quadratic term, you can just write all that things. Gradient. Okay, this is the first gradient, this is the second gradient. And if you fix the all other gradient, and so you have a one-dimensional problem, is that xi, wi, so this is the constant, this is a constant, and this is, you just have delta I, and the i's gradient of the x, and the next term is the i's diagonal of the Hessian matrix. So now you want to find the optimal delta I to that coordinate. And so this is a quadratic term. You have closed form solution. The problem is that, okay, you have here wi plus delta I. Okay, this is make the things a little bit complex, but it's fine because you can easily write. It's a quadratic term, and you can rearrange something, and you can easily see it. You have on that case, it's proximal to delta I.
So the variable is W or X?
Oh, sorry, it's W. Yeah, because X is used as a training set. the i's divided by the first gradient divided by the second order gradient. Okay, this is the quadratic is here, and you can write, and you can add a wi here minus a wi here. You see, okay, it's a proximal operator, so you can see that equals to wi delta I plus wi minus w. Okay, you want to find an optimal delta I. You just think it's a y. It's a y. And you just, so you, on general case, you just solving arc minimum. You have a, sorry, and plus a quadratic term. Minima here. So you solve this problem. So, and this is the quadratic term, this is a long smooth term. And fortunately, you have a closed form solution. It's called the soft shrinkage. So the closed form solution is that equals to x, the absolute value minus eta delta, and the positive part times the sine of x. So on the fig, this is the origin x, and what is the soft shrinkage operator is that you reduce the value of x by lambda over c eta, and if that value is more than this, then say okay, you get 0. So for the small x, it goes to 0. For the large x, you minus the absolute value. So it's a soft shrinkage operator. And so that is coordinate descent. So you have, each time you pick up a coordinate and solve a closed form solution. And now let's move to a more general setting. So we consider a more general setting that, sorry, it should be W. For general fx, and this is still a long smooth term, a smart regresser here. If we want to solve that thing, for example, this is hinge loss is not okay. It's squared hinge loss or logistic loss. So if that you have second order gradient, you can easily find. And so for the general f, you usually do not have a closed form solution on the ith coordinate. What you can do is that you can approximate f by a quadratic term. So you can approximate equals to you can use a second order approximation. So if you do that, so now you can solve, if you can solve a quadratic and you can turn to the coordinate descent solver. So on most cases you do not, and this can be done because on coordinate descent, each time you only look at one coordinate. So you don't need to compute this huge Hessian matrix. So it's quite cheap. And on some cases, you do not want to have the second order gradient. You just have an upper bound. So usually U is greater equal than the Hessian matrix one possible is that you can just choose the second order matrix, or the other case you can using Li. L is the Lipschitz continuous, so it is greater than the Hessian matrix. So you can have this term will be upper bound of the f, and each time you minimize the upper bound of the original object function and you solve it. So, and on this algorithm, you do not have many to tune. One is that how to select the coordinate. Usually, I think the past 10 years, people have tried to look at, okay, which one maybe you want to solve first. But on generally speaking, okay, people find on practice, you just randomly pick up a coordinate, it works great. On average, and you beat everything. The other case is how to choose U. One example is, yeah, you can use a fixed U here. The other case is you can have that one, but if it depends, it really depends on the data. So if each coordinate have an average almost the same variance, so in that case, your Hessian matrix is quite uniform. So the terms on that diagonal is quite similar. You can just use the average L here. But on that, if it is not the case, for example, for the text data set, maybe you have some coordinate have a lot of non-zeros entries. For example, if you use a back of forward feature, so this feature maybe is the Z or I, R. So in that case, that feature have a lot of non-zero entries. So in this case, the variance of this feature will be very large, and you have a very long tail. So in that case, the values on the tails may be quite small. So using a uniform L is not a good idea, because if you compute a gradient on that thing, the first gradient, you have a very large gradient, you have very small gradient. So if you use a very large learning rate, you do not converge because that value is too large and it blows anything up. And if you use a very small learning rate, okay, you have a very slow conversion on that tail part. So, and I think that is one of the reasons that why coordinate descent is good, because you have a per coordinate learning rate. Your learning rate at each coordinate is the second order gradient, or you have an upper bound here. It's adaptive to the coordinate. And also you can have, I think John Ducci have a paper about adaptive gradient. So each time you still have a diagonal here. The diagonal is, the diagonal is your summation over all the past gradient, or time 2t, and this is all the per coordinate operations, and the diagonal is equal to here. So this is the same things. If the gradient at the past gradient is very large, you will divide by a very large value, and you drop the values down. If the values gradient at the past is small, you just, you increase the learning rate size. So, and on practice, on deep learning, I think people use that because Jeff Dean write a paper, say, okay, that works great. And it really depends. Yeah, it works, on average, it works fine, but maybe if you can compute the second order gradient, maybe it works better. And you can also compute the upper bound of the second gradient. For example, trusted Newton method or something like that. Okay, so the next things, how to solve a more general optimization problem. So given that fx and for the passive, if it's convex and you have a sparse regression here, you have 1/t converge rate. But if you move to the non-convex things, you cannot show you have how fast you converge. You can only show, okay, you converge to a stationary point. So the next problem is that given a non-convex, it may be non-convex. And it's convex, but maybe non-smooth. So how to solve that problem? So remember that Soviet have set proximal gradient. So coordinate descent, yeah, on that form, it's just a special case of the proximal gradient. The difference is that now you do not solve all the coordinates at the same time. Each time you only update one coordinate. So let me see how we can do that. And still the generally, okay, look at that things. So if for the general case, it's still fine. Each time you're solving, yeah, this is the new value of the W. You're solving U. So now on the case, you still have a quadratic here. U is the upper bound of the Hessian matrix. It's a matrix. And this is the inverse of the matrix. This is the gradient. This is the first order gradient. And you should have, maybe you use a V here. Yeah, okay?
But you have a norm square at the back. You do not have the left bracket.
Oh, yeah. It's fine. It's a vector.
So the left means that you do not have to land on that anything on the
Oh, yeah. Sorry. Yeah, it should be good there. Okay? And so comparing to the proximal operator, this is slightly different because on that thing you have a U here. U is on the previous assumption, you just have a scalar. You do not have a matrix here. Now you have a U here. This is a small trick that you can hack the longs. You can using I forgot the name. Mahalanobis, no? So, yeah, is that this norm is for given a positive definite matrix is equals to X. So on that case, you can just remove the U here and right here. U is the upper bound of the Hessian matrix, the second order Hessian matrix.
Okay.
So on that case, you have adaptive linear rate at each coordinate. So if you solve the problem at the full time, you just a Newton method because it's Hessian. And if you solve the coordinate descent, each time you only solve one coordinate of the Wi. And it's still workable, even you have very complex edge here. Okay, is that clear?
How do you solve for only one coordinate of W, since you have a U inverse in there?
Okay, so if you look at the ith coordinate, you only look at the ith diagonal of the U.
Okay.
You can ignore the others. So on the other case, each time you cannot compute the U. And on this problem, you still want to how to choose the U. One is that you still want to have you have L equals Li. L is the Lipschitz continuous.
Is U assumed to be diagonal?
So if you're using coordinate descent, the original coordinate descent, each time you only solve one coordinate, so you do not matter. It doesn't matter. So you only want to compute the diagonal of the U. But if you do not, maybe you can solve a block several at the same time, you need to consider about that. You can still using diagonal things, and you can using approximation of that block His matrix. For example, you're using LBF.js, so it depends. But on most of the cases, I will turn back to the topic later. So how to solve multiple things at the same time.
Also, is you adaptively chosen every iteration, or is like this is constant that you're choosing higher?
Yeah, you need to adaptive to compute the UI the runtime. Each time you need to update the U. And each time, in fact, you want to compute the gradient and you want to compute the U. So all the coordinate things, you need to compute two things for each. So the first order gradient I at coordinate I, and maybe the second order gradient at coordinate I, or upper bound of it. Okay? So let's move to the parallel things. Sorry?
You are computing the Hessian every iteration. You said you plus 2 compute.
Yeah, you need to compute that, but you only want to compute a part of the Hessian matrix, only the diagonal things.
But to compute that particular thing, you have to compute the gradient first, and then you compute a part of that, right? So you have to compute the whole gradient concept, every iteration, and then a part of.
Yeah, the whole gradient and the part of the Hessian matrix. It's double. It's just 2 times expensive than ordinate gradient descent, because you only want to compute the diagonal things of the Hessian matrix. Okay, the next thing is that it's a sequential algorithm. So it's faster because it's a sequential. So because for the next coordinate, you see what is the update of the previous one, and you see the result, and you can choose the right direction. So that is one reason why it works great. And or maybe, yeah, that is also the reason why Gibbs sampling works great, why stochastic gradient descent works great, because it's each time you only solve a small problem and you have a lot of iterations. So, but the bad thing is that you cannot easily have a parallel implementation, because each time you only look at one coordinate descent, and if you want to, you have 2 options. One is that you make each coordinate as a multi-thread version. So if your data is really very, so you have a matrix, each time you only look at one column. So if the matrix is really large, and so you can have, you can implement by multi-thread. You can have 4 threads, each one update one part of it. But you need to pay the thread synchronization. And if you have millions of billions of features, you need to pay millions of billions of thread synchronization. It's not thorough. It's not a good idea. The next, the next option is that, you can update multiple at the same time. Remember that how to parallelize the stochastic gradient descent, you just use a mini batch. You update several samples at the same time. On this case, you can still do that things. So we first talk about the shared memory cases. So this matrix is on one machine's memory, and all the thread can read and write all the things of the W, of the X, of the W, all the things can be right. So the first algorithm is called shotgun. It's a very simple idea that, you just if you have P thread, each time you work on the one coordinate. If we finish, you move to the next one. So you just simply have a multi-thread work on the multiple things. So this is from 2010, I think. It's from Carlos Gaston's group. So the problem is that because if several threads work at the same time, you cannot see what the other thread update immediately. So you maybe make the wrong decisions. So we can what we can see is that, so we consider two cases. One is the optimal case. You have a diagonal x. So each feature is not correlated. So at that time, this thread update thread 1, update coordinate 1, thread 2, update another coordinate. It's fine because they do not relate to each other. You can have as much thread as possible. Is that okay? Because you want to compute the gradient, you don't need the value of the other coordinate. You can compute the gradient, you can compute the second order gradient, and you can update. That's not related. So, but the worst case is that you have all the features are the same. So on that case, if you have, for example, 3 threads, P1, P2, P3. Okay, so the first case is that if you only have one thread, maybe you want to update this W by delta, this is fine. But if you have 3 threads working at the same time, so if they really start computing at the same time, so finally there we have got, okay, 3 updates, each to delta to the different values. So that is a problem because all the features are the same. It's equal to have one coordinate has 3 times delta things. So it may be, you just increase the learning rate. It may be dangerous. So if the features are less correlated, you can have as much thread as possible. But if the features are correlated, so you cannot have so many threads at the same time. You need a lot of synchronization. So how to analyze the data structure? One possible thing is that you can look at the largest eigenvalue of the covariance matrix. That is this term. This term indicate how correlated of each features. On these cases, it's equals to P, equals to N. For example, if you have N features, for these cases, it equals to 1. Because all that things are correlated. And yeah, I have normalized all the things. I have normalized all the other things. So if this one is large, you can have as many threads as possible. So if this one is small, you can have only one thread. So you should choose the number of threads smaller than this value. This is what shotgun about. So you first look at the covariance matrix, compute the largest eigenvalue, and then decide how many threads you want to have. The next thing that, okay, I still want to use as many threads as possible because maybe you just there's some situation in that case. It's true on the distributed computer, but it's not really true on the parallel setting. But first imagine that, okay, I still want to have P thread, never regard what it is. So what do you want to do? So for example, you want to have 10 threads. You have 10 threads, and you want to use all that thread you have. So what you can do? A simple case that, so even that thread work at the same time and get the delta. And you can still using a small learning rate. Okay, you compute the delta and you can place an additional learning rate here. And so that each thread only contribute, for example, in this case, eta equals to 1/3. So you just use a small learning rate to guarantee that you do not blow things up. Okay? So how to choose that thing? Okay, you can using eta equals to a minus rho. So rho is the largest eigenvalue. So in this case, rho is equal to n. So you can have the largest learning rate you can have equals to 1. On this case, okay, equals to 1, and you only can use a very small learning rate. And on practice, the good thing of this method is that you can say, okay, this is how many threads we have, and we choose it. The next thing is, okay, we have to choose the learning rate. On most cases, this is just a loose upper bound. You can have a more aggressive learning rate. Even rho is quite small, maybe you can still have a large rho, because rho is just one perspective of the data. Maybe you have the data is not so ideal, so you can still have a large learning rate. So in that case, this is the tuning parameters, and you can tune it. So this is one good thing of this method. And on practice, you can have really large theta here. Okay, but on practice, you want to choose on that way. On practice, you can increase a little bit, so you can have a fast converge rate. Okay, so this is the parallel things. And there's another papers about how to optimize that thing. You can asynchronise the things, but I don't think it's not worth to look, because it's all about theories. On practice, I think this is fine. On theory, you can work on a lot of things, but the theory is quite messy. And now let's move to the distributed version. So on that case, you do not assume the X is on the main memory. You have very long, very large rows and very, very large columns. I think the average, what the size of the industry now is, you have 100 billion of rows and 10 billion of features. So this is almost the state of the art for the industry people. And so you cannot have that things on the memory. So you need to divide the matrix onto multiple machines. So you have two choices here: partition by rows, partition by columns. So we first look at how to partition by columns. So this is the X you have, and maybe you have 4 machines. You can partition by 4 times. So each part go to 1 machine. Machine 1, machine 2, machine 3, machine 4. And now, because you have the whole data of that coordinate, that machine can control a part of the W. So this W goes to this machine's memory, and this data goes to this machine's memory. And now what you can have is that, okay, because you have all the data of that coordinate, you can just, that machine can update that coordinate by yourself. You do not. For the original method is that, the simple method is that, okay, each machine randomly choose a coordinate, update its values. Okay, there's no communication. But this is not good, because if we want to compute the gradient, you need to know what is the others want to have. So this is, if you do not want to know the others, that you solve a sub-problem independently. So maybe it's not a good idea. But if you want to know what the others, you need to do communications. So what do you want to communicate? You cannot ask that the W from the others, because you do not have that data. Even you get the W, you still cannot compute the gradient. The good thing is that, okay, you only need to know the dual variable. For Lassau's case, is that only W and X. So you want to know, so each machine computes its local dual variable. So xi, wi, you just compute xi times wi. And each one have its own dual variable, and you summation over all the dual variable, and you get the global things. And once you get the global dual variable, you can compute, and this machine can compute the exact gradient for for the coordinate it maintains. So what you want to communicate is that it's this long vectors. And if you do not consider practical things, on that case you can show that the converge rate is great, and you can increase you have more machines and your converge rate goes on. But on practice, you cannot synchronize that vector because it's very large. For example, if you have 10 billion, 100 billions of it's how large? So you cannot compute that things. So what you can do is that, okay, you can communicate from time to time. You cannot communicate you cannot wait maybe you can, pass one data, pass the whole data once, and then communicate the things once. This is a BSP model. That is, each machine starts from maybe the left side of the coordinate, and you pass it the whole time, or do that at the same time, and wait. Okay, now this time we communicate with each other to get the new value of the dual variable, and then we start compute again. But because it's very large, you need to pay a lot of time during the communication. So you can have another thing, asynchronous things. You can have the computational thread run that, update that at the same time, and then you have another I/O thread. You can send and receive the things. And what you can even have is that if you have a large delays of the others. So if the coordinate really do not correlated, so you don't need to get the immediate data of the others. So if you have that things, okay, you can design a very nice protocol. Machine 1 send data to machine 2. Machine 2 get the data from machine 1 and aggregate at the new data from its own, send to machine 3 and by a ring. So in this case, you minimize the communication, but you increase the delays because for this machine to get the new update of that machine, you need to pass the whole machine for once.
I got a question. How exactly do you arrive at the dual variable? Do you use some kind of ADMM type of dual decomposition? So how do you compute the gradient based on the dual variable?
Okay, for Lasso, it's quite simple. For Lasso, how to yeah, for Lasso that this is the dual variable, and if you get the dual variable, you can use its own data to get the full gradient of that coordinate. Because so on the general case is that if you have on that form, maybe you have y here, we just ignore the y. So you want to compute gradient. It's the gradient of f times, this is a dual variable. This is a long vector, and you get a part of x. So you need to compute these things. And it depends. Maybe you can sum over it. It can be decomposable. You can sum over it, but maybe not. It depends on the problem. So you need to compute these things. And you can have ADM type things. You can have loose. The ADM things, you do further decompose the problem. So you can allow a lot of delays on the ADMN, but you pay a cost because you have slow converge rate.
So is ADMM seems to be converging in case of
Yeah, ADM converges, but the speed is quite slow.
For the synchronous case, it's theoretically guaranteed to converge, right?
And yeah.
So asynchronous, I don't think it's guaranteed to.
I think there's some paper about the asynchronous ADMM.
There is?
I think yeah, but I don't. On practice, I don't know. I do not sure.
Okay.
So how fast it converges then it really matters. Yet every method converges.
But the thing is, even for the normal ADM, the convergence rate is not known. Is it for this normal synchronous ADM?
It's 1/t.
1/t?
Yeah, I think there's some paper to prove that. But I didn't go through the proof because it's quite long. And the next step is that you want to. So the bad thing of this is that this vector is almost a dense, and especially you have a real large of samples. You really need to communicate a lot because this is dense. And the next thing is that, okay, we can partition by rows. So each machine can have a part of rows. Machine 1, machine 2, machine 3. So if we want to, so this is a global, W now is a global shared. The good thing is that you can have the dual variable. You can compute the dual variable if you have the whole W. On some cases, you can have it because the data is quite sparse. You only want to get the value, you have non-zero features. So even that is 100 billions, you really get a small number of rows. So the non-zero patterns is not so large. You can still cache all the W's you want. You can have it in your memory. So each machine to get the copy of the row, the columns you want in your memory. In that case, all the things you can fit into the single machine array. If you do not, you just increase the number of machines. But the bad problem is that you need to, if you want to compute the eyes things, you need to have a synchronized between all these machines, because you need to sum over all the samples for this column. So you need to get all that output of each machine. So, and on that case, you cannot. The synchronization cost is really large because you transmit the data and transmit the data back. It costs one ms or millisecond. So if you have billions of coordinates, you just pay hours or to the synchronization. So what you can do? What you can do is that, okay, on that case, you need to update the block of the coordinate at the same time. So on that case, each time you pick up a block of coordinate, each machine compute the first gradient of that block. Maybe you want to compute the diagonal of the second gradient, and then assume this vector. This is a global shared vector. You maybe sit on some servers. We usually call it a parameter server. And this machine all send the gradient to that centralized server. And that server aggregate all the gradient and do some update and tell us, okay, this is the update of that things.
But you can have this thing without a server, right?
No, you don't need to have that one. You can have, okay, you can make one machine be the root.
Go in a cycle.
Yeah, cycle is fine. And you can go cycle, you can go tree, or you can go anything you like.
But like between these two, having a server and not having a server, right?
It does not matter.
But for example, from the perspective of say, when one of the machines fail or like when things go wrong, which one? What's your opinion on like which one is better, going server or going?
So if you have server, it's an easy problem because you just guarantee the server side is fault tolerance. Maybe you have several servers here, you do backup. So each server die, you still have a backup. And this is the worker machines. For each worker machine die, you just add another worker machines. So you can just throw this machine because you just throw a part of the data. You can still, if you have a coordinate descent, you can just the first order divided by the second order. The quantity is still unexpected is fine. So if you do not care for tolerance, you don't need to have a server actually. You just use the MPI. You have all reduced over that things and you aggregate by tree. So the next thing is that, okay, you still need to pay a lot of synchronization because on the BSP model, you calculate the gradient, send it, and you wait. You wait that the server, may assume that's a server. You wait the server get all this gradient and send the data back. So this is a long gap. So you need to wait a lot. And because you have a lot of blocks, you still need to wait a lot of times. On that case, okay, you can have a little bit of asynchronous here. So what you can do is that, okay, if at time 1, all the machine computer on the block 1 send out the gradient. And then now you do not wait the gradient back. You can move to the next block, maybe this block. And you still compute the gradient, send it out. And wait. I do not wait, you can move around. And you cannot, now there's two options. One is that, okay, you do not care about anything. It's the eventual consistency. You can just move around. If data is back, you get it to update to your local memory. If not, you just keep around. The other thing is that this, on practice, it works fine. For example, if you know Yahoo LDA just use this step. The next thing, okay, you want to, for the theory aspect, it's not good idea because maybe you have one node is die, so you don't know essentially, so you do not get anything back. So on theoretical, you can assume, okay, you have maximum delays. You can have delays, so you can allow almost a tau block is not get the data back. If the number of blocks not update exceed this number, you stop and they wait something. So on this case, though this is still back to the shotgun setting. So if this block is not correlated, so it's safe because you compute these things do not require the value of that blocks. But if it's correlated, it matters. So, and now the delays. The delay, that means you have multiple blocks. If they are correlated, you have collision with multiple blocks. So we can back to that trick we discussed earlier. On that case, you can use a small learning rate. You can tune the learning rate. So in this case, you have the machines is fixed. What you can do is you choose the tau, and you can choose the learning rate. So on practice, the learning rate is that P, you still have the equals to, rho divided by n. This is the correlation between blocks. Maybe this is the number of blocks you have. And you still need to, okay, times the tau. This is the delay you need to pay. It's not, sorry, I forgot. It should be times. So if we do not, it's tau plus 1. So if tau is 0, you do not you do not allow asynchronous things. You still have this number. If you increase the number of sets, you need to make sure, okay, the learning rate is on this scale. But on practice, you can choosing how theta it is. It depends on the data, depends on the network condition, it depends on a lot of things. Okay? So I think we only have 1 hour. Is that right? Yeah, sure. We are almost done. So, okay, let's have a quick review. Okay, we talk about coordinate descent. Okay, I think it's 10 years ago, people find out, okay, coordinate descent is really good at solving lasso because 10 years ago, machine learning community is really fascinated by lasso. And then you have group lasso, and also coordinate descent works fine. And then the liblinear used coordinate descent win the 2008 linear classified competition. So it get be famous, and they write a review article about how to classify a text classification, and they show that okay, coordinate descent works really good. And then now that on the past several years, people working on the coordinate descent, and because for the theorized things, okay, everything's here because it's order algorithm. If you want to have a parallel things, you need to do a lot of tricks. Just like a stochastic gradient descent. If you want to run a parallel things, you maybe have a mini batch, or maybe you have another things, do averaging or something like that. So, so we had talked about coordinate descent, how to solve a general problem, how it related to proximal gradient, and how to have a parallel. On the shared memory, you can just have multiple threads work at the same time. If you have multiple machines, you need to pay a lot of attention to how data is communicated and how to hide the delays. Okay? So okay, that's all. Thanks. Thank you.